Hi, welcome to lesson 29, session 3. Today we're going to be continuing working on our classifying two-dimensional figures. Today we will specifically be using tree diagrams. In the past, we've been using Venn diagrams pretty heavily. And so today we're going to be doing the same classifications, but we'll be doing it using a tree diagram. So we're going to go ahead and get started. We'll be working on our Ready Classroom Math Workbook on pages 597 through page 602. Wow, 600 pages of math already this year. Great job for making it this far. Go ahead and turn to page 597. All right, on page 597, we see that we have, it says to read and try to solve the problem below. Make a tree diagram to show the hierarchy of the following shapes based on their properties: rhombuses, trapezoid, polygon, square, quadrilateral, rectangle, parallelogram. Use the exclusive definition of trapezoid in your diagram. A trapezoid is a quadrilateral with exactly one pair of parallel sides. Then classify these shapes into as many categories as possible. So first of all, let's go back and kind of break apart this problem to see what it is that we're solving. So we know that we're going to be making a tree diagram. We know that that tree diagram needs to have rhombus, trapezoid, polygon, square, quadrilateral, rectangle, parallelogram. We're going to use the exclusive definition for a trapezoid. So just write exclusive, meaning that there are exactly one pair. This is the one that doesn't love everybody. It wants to be separate. So first of all, we're going to look, and then when we're done with all that, then we're going to deal with these shapes, but we'll do that in a moment. So let's start off with our shapes. Now we need to start with what of these shapes listed above is the most general. It's the one that's always at the outermost oval that we work with. And we've been doing this for, quite a few days now. So you should know what is the most general shape we have that's listed here. That's right, it's the quadrilateral. And then we're just going to put a rectangle around that quadrilateral. It helps to go ahead and write the word first and then draw the box around it, just because it just is a little bit easier, because otherwise you're trying to fit all the word inside the box, and if you don't draw the box big enough, then you've got to start over again. So just do that first. From there, oh my goodness, I made a big mistake. Who can see my mistake? That's right. There is a shape that's even more general than what I wrote. So I'm going to go ahead and I'm going to erase it and start over again, because I want to make sure that I do this the right way and it looks like it wasn't an afterthought. Okay, so many of you may have already caught my mistake, but when I looked up here, I realized I saw this word right here, polygon, that I didn't recognize that it was there. Remember, a polygon is any shape with 3 or more sides. So a polygon is actually even more general than a quadrilateral, because a polygon only has to have 3 sides. And then a subcategory of polygon is going to be quadrilateral, because all quadrilaterals are polygons, because quadrilaterals have 4 sides. Polygon has 3 or more sides, therefore a quadrilateral is also a polygon. From there, this is where we're going to see a little bit of a branch off. Now, we know that we're going to see parallelograms, because we know that a parallelogram is the next most general shape. So we've already got polygon, we've already got quadrilateral. And so we know that parallelogram is going to come next, because we've done this for a few days now. Now, the reason that I didn't put trapezoid next is because we're saying a trapezoid is a quadrilateral with exactly one pair of parallel sides. Parallelograms have two pair of parallel sides. So a parallelogram can never be a trapezoid. So we're going to go ahead and we're going to put the trapezoid over here all by itself. Because a trapezoid, it wants to be exclusive. I'm going to write the word exclusive here. It wants to be all by itself. It wants to say that it can only have exactly one pair of parallel sides. So a trapezoid is a quadrilateral, a trapezoid is a polygon, but a trapezoid will never be a parallelogram, nor will any other shapes fall under that trapezoid category because it's being so exclusive. Now, now we have, all right, so we've got our trapezoid now. So now we have left rhombus, square, rectangle. Okay, so remember that we know that the square is the most specific. So it's going to be down here at the bottom. But if you remember back from our Venn diagram a couple lessons ago, I don't remember how long ago that was, we talked about, maybe on the first, let me go back. No. Here we go. We talked about the attributes of a rhombus and a rectangle and a square. And we recognize that a rhombus can never be a rectangle, and a rectangle can never be a rhombus, but they both can be a square. So this is what it's going to look like if we were drawing it as a tree diagram. We're going to have a rhombus here, because a rhombus is a parallelogram. And then we're going to have rectangles here, because rectangles are also parallelograms. So a rectangle can be a parallelogram, it can be a quadrilateral, it can be a polygon. A rectangle cannot be a rhombus, and a rectangle cannot be a trapezoid because they're not connected. And then this is the fun part, in my opinion. Then we have square. Now we know that a square can be both a rhombus and a rectangle. So we're going to connect the rhombus to the square to the rhombus and the square to the rectangle. Now, when we look, if we follow this line, a square can be a rhombus, a parallelogram, a quadrilateral, and a polygon. A square can also be a rectangle, and because it can be both, okay? A rectangle can only be a parallelogram, a quadrilateral, and a polygon. A rectangle can only sometimes be a square. A trapezoid is always a quadrilateral and always a polygon, but a quadrilateral can only sometimes be a trapezoid. Exclusive trapezoid, that is. All right, so now we're going to look at shape A and shape B and see what we could classify it as. So we're going to write shape A. Now shape A has four sides, so it can be a quadrilateral. Shape A, does it have, and a polygon. I keep forgetting about that polygon, man. Okay, so shape A can be a polygon because it has at least three sides. It can be a quadrilateral. Can it be a trapezoid? Exclusive trapezoid. No, because it has two sets of parallel sides. So they're excluding this as a exclusive trapezoid. Is it a parallelogram? Yes, it's a parallelogram. It has two sets of parallel sides. So it could be a parallelogram. Oops. It can be a parallelogram. All right. Can it be a rhombus? Does it have four equal sides? Yes, it can be a rhombus. Now, since it's a rhombus, can it be a square as well? A rectangle as well? No. Can it be a square? Yes, but in order to be a square, it has to have what? That's right, 4 right angles. Do you see any right angles? I don't. So it cannot be classified as a square. So shape A can be a quadrilateral, a polygon, a parallelogram, and a rhombus. Now let's look at shape B. Shape B can be a polygon because it has at least 3 sides. It can be a quadrilateral because it has 4 sides. Can it be an exclusive trapezoid? So it has one set of parallel sides. Is this side parallel? Nope. So it can be an exclusive trapezoid. Can it also be a parallelogram? No, because it only has one set of parallel sides. And in order to be a parallelogram, it would need to have two sets of parallel sides. So shape B can only be classified as a polygon, a quadrilateral, and a trapezoid. All right, let's go ahead and go to the next page. All right, on the next page, we see that we have the same problem as above. Now, we drew it as a tree diagram, but you can also use a Venn diagram to be the hierarchy of shapes. So this outer rectangle are polygons. This big oval is all quadrilaterals. And then we have a small oval that's trapezoids, and this is exclusive. So remember, it cannot be parallelograms cannot be trapezoids. So this oval and these ovals are totally separate because they cannot overlap even at all. And then all parallelograms, all of these shapes inside of parallelograms can be classified as parallelograms. And then we have rhombuses, squares, and rectangles. So all squares are rhombuses, all squares are rectangles, all squares are parallelograms, all squares are quadrilaterals, and all squares are polygons. But squares are not exclusive trapezoids, because squares have two pair of parallel sides and exclusive trapezoids only have exactly one pair. You can also show the hierarchy among shapes with a tree diagram. Now, this tree diagram is the exact same tree diagram that we drew. The only difference is we drew ours vertically, meaning going up and down. And here they drew the tree diagram horizontally, or going from left to right. But it still stays the same. We have polygons, we have quadrilaterals, we have exclusive trapezoids, we have parallelograms. See what I mean about trying to fit it in the box? We also have rectangles, so we know that this must be a rhombus because a rhombus can never be a rectangle. And then finally, the most specific shape that we talk about, other than maybe arguably the exclusive trapezoid, is the square, because the square has all of these attributes, except for the trapezoid, all of these attributes, but it cannot be an exclusive trapezoid. All right, let's make some connections. So when we look at the Venn diagram up top, which part of the diagram shows the most general category? Which part of the diagram shows the most specific category? So typically the most general is going to be the biggest shape that's out there, and the most specific is going to be the smallest shape that you can see. So the outer rectangle shows the most general category, which is polygons. The sections that have no subcategories inside them are the most specific, which would be the trapezoids and the squares. So if we look over here, the most general is polygons because they are the biggest shape. And then the most specific are the ones that are either by themselves, well, they're both by themselves, and they have nothing else that's inside of them. That means that they're the most specific. So trapezoids and squares are the most specific. How is a tree diagram similar to the Venn diagram? How is it different? So both show the hierarchy of shapes from the most general to the most specific. So Venn diagrams and tree diagrams are going to start, a Venn diagram starts with the biggest shape and goes to the smallest shape. A tree diagram starts either at the top and goes down, or starts at the left and goes to the right. But the Venn diagram shows this by regions, and the tree diagram shows this by branches. So what that means is a Venn diagram shows like this is a region, like an area that's covered, and then each of the areas inside of it go inside of the most general shape. And over here, it shows like branches of the tree talk about how it's all together. Number 3 says, how can you see all of the categories that a shape belongs to in a tree diagram? What are all of the categories that shape A belongs to? So each shape belongs to the category that comes before it. Shape A is a rhombus. It's also a parallelogram, a quadrilateral, and a polygon. But remember, it's not a trapezoid because it does not have exactly one pair of parallel sides. Why do the branches that come off rectangles and rhombuses both lead to the square? Both rectangles and rhombuses, not rectangles. Oh, that's not what I meant to say. Both rectangles and rhombuses have four sides and two sets of parallel sides and a square shares equal sides with a rhombus and four right angles with a rectangle. So the reason that the branches come off rectangles and rhombuses both lead to square is because both rectangles and rhombuses both have four sides and two sets of parallel sides. But then a square shares the equal sides with a rhombus, which the rectangle doesn't have. And the four right, that says right, not 8, looks like 8. Let's write that again. And four right angles with the rectangle, but the rhombus does not have the four right angles. And then we're going to explain the relationship between the properties of categories when you move left or right or up and down on a tree diagram. So if you have a tree diagram, when you move from top to bottom, like as you move down, you get more specific. As you move up, you get more general. On this one here, as you move to the right, you get more specific, or to the left, more general. Now this one this is the inclusive definition of a trapezoid. So this definition of a trapezoid here would actually, it makes it all go together. If it were the trapezoid that is exclusive, you would see a box that would come off over here, off of quadrilaterals, and this would be the trapezoid, which is exclusive. And because it has four sides and exactly one pair of parallel sides. So that's where this trapezoid would go. All right. You may want to, let me zoom out. You might want to screenshot that to help you out. It may help you out later today because this is the hierarchy of quadrilaterals, starting with polygon, quadrilateral, exclusive trapezoid, inclusive trapezoid, parallelogram, rhombus, rectangle, square. All right, so now we're gonna go ahead and, let me finish this one. So all properties of the level to the left meaning if you're talking about quadrilaterals, all the properties of this shape to the left are also true of the shape, the level you are on. So a quadrilateral also has all the attributes of a polygon. A parallelogram also has all the attributes of a quadrilateral and a polygon. When you move to the right, or moving down, if it's on the like the one we drew on this page here that goes up and down, you move to a category that shares all of the same properties, but also adds additional properties. And then finally, on the reflect, it says, do you prefer to draw Venn diagrams or tree diagrams? And it could be either type of tree diagram. So tell me which diagram you prefer, and then tell me why. When you're done doing that, you're going to go ahead and go to page 600, and we are going to go and do number 7, 8, and 9. So on number 7, on page 600, it says this: Cyrus made the following tree diagram to show the relationship among scalene triangles, equilateral triangles, and isosceles triangles. Is his diagram correct? Explain. So I want you to look at these triangles that are written here and think about the attributes of those triangles. I'm actually going to show you a triangle hierarchy that I created so that you could kind of see what the hierarchy of triangles is. So, like quadrilaterals, we start at a polygon because a polygon is any shape with 3 or more sides. Then we go to a triangle. A triangle is pretty general. It has 3 sides and 3 right angles. An isosceles triangle has 3 sides and at least 2 of the sides are equal. A scalene triangle has 3 sides, but no sides are equal. So a scalene triangle could never be an isosceles triangle because an isosceles triangle has to have at least 2 sides that are equal. Then you have a right triangle. A right triangle has 3 sides and it has 1 right angle. It's possible for an isosceles triangle to be a right triangle because it could have 2 equal sides. It's also possible for a right triangle to be scalene because it could have a right angle, but it could have 3 sides that are all different lengths. And then the most specific would be the equilateral triangle, or arguably the right triangle could also be the most specific. But we've got the equilateral triangle has 3 sides and 3 sides are equal. So all the sides are equal in an equilateral triangle. So I really want you to look at this line here and to see, because I think we had the triangle, isosceles, scalene, equilateral. So now look at the one that was drawn for us, and what do you notice? That's right. They're asking, is this diagram correct? And you're going to say, no. The isosceles triangle and the equilateral triangle are switched. Equilateral triangles are the most specific. Because they're the most specific because in order to be, so we need to switch these two. Because isosceles triangles only need to have one set of, or I'm going to change that. I don't want to say one set. Isosceles triangles need to have 2, at least 2 equal sides. Equilateral triangles need 3 equal sides. So that's why the equilateral triangle needs to be down below and the isosceles triangle needs to be up top. The other two are right where they need to be. All right, when we're looking at number 8, this isn't going to help you anymore, so I'll go ahead and move that to the side. Number 8 says this: an equilateral triangle has 3 sides that have the same length. An equilateral triangle may also be called an equiangular, that's a hard word to say, equiangular triangle because each of the three angles has the same measure, 60 degrees. Insert an additional category in the tree diagram for equiangular triangles. Explain. So we know that triangles have three sides. Acute triangles have all of the sides are less than 90 degrees. A right triangle has one side, one angle that is 90 degrees, and then the other two can be something else, but one angle has to be 90 degrees. And then an obtuse triangle has one side that the angle is greater than 90 degrees. So there's one that's much larger. So if we're looking at trying to find a triangle that has all three angles that are 60 degrees, meaning less than 90, would it be acute, right, or obtuse? That's right. It would be classified as an acute triangle. So we would put the equiangular triangle here. Because an equiangular triangle has all three angles that are less than 90 degrees, which is what an acute angle is. An acute triangle is. So now, so we don't need to say anything. We just need to put it there. Now, well, I guess we explained it, but I just explained it, so you're good. You could just say an equiangular triangle has all angles that equal 60 degrees. Acute triangles have all angles less than 90 degrees. So now if we're looking at the tree diagrams and the two problems above, so we're looking here and we're looking here, what category are the categories of shape E has all sides of the same length? What are the categories of triangles to which this triangle belongs? So first of all, if we're looking at all of these words, okay, is it a triangle? Yes, so we know that this can be a triangle. Now, can it be a scalene triangle? Remember, a scalene triangle has no equal sides. Nope, we know that all the sides here are equal. So since they're all equal, we know that it cannot be a scalene triangle. Can it be an isosceles triangle? An isosceles triangle has at least two equal sides. Yes, it can. So it can be isosceles. Can it be an equilateral? Oh, definitely, because we know that all the sides are the same length. So it can be an equilateral. All right. Can it be an acute, a right, or an obtuse? Well, there's no right angles. There's definitely no obtuse angles because it would need to be much larger for that, but they are all definitely less than 90 degrees. So it can be an acute triangle. And then because all three sides are equal, that tells us that also all three angles are equal. So it can also be an equiangular triangle. And with that, you're going to go ahead and do pages 601 and 602 on your own. And then if you have any questions, email your teacher. And I will see you next time.